Okay, so chapter 3, section 6 for algebra, we're solving proportions using cross products. We did this yesterday when we were reviewing proportions. Bless you. We were using the cross product property, weren't we? Okay, so if we review that real quick, we could have like W over 3 equals, I don't know, somebody give me some fraction that could equal. Dylan.
7/9.
7 over 9. Okay. So this is something that we could just blow up. In other words, 3 times what is 9?
3.
3 times 3 is 9. So something times 3 is 7, which is a little tricky, huh? Since that's a little tricky, this probably is a good place to use our cross products. So Dylan, what do we do to use that?
You can multiply 3 times 7.
Okay, so we bring the 3 up next to the 7, 7 times 3. And we bring the 9 up next to the W, 9 times W, right? And so we end up with 9W equals, everyone? 21. And then how do we isolate the W? Divide, good. And so this is a little bit tricky. I don't know how we could write this just as a mixed number, right? Or we could change it to a decimal. When we have 3's in there, often we have a repeating decimal. So how many times does 9 go into 21?
2.5 times.
2, and that's 18, right? And there would be how many left? 3 9ths, which is 1/3. 3 9ths is 1/3. 2 1/3. So rather than leaving it as a repeating decimal, we'd probably leave it as a fraction. Okay, so that's kind of the process that we're talking about. The first thing we do is bring this says that the cross products of a proportion are equal. So here's the original proportion, and when we bring the denominators up and multiply them with the opposite numerator, we have an equal statement, right? An equivalent statement. So here we have it as a rule. Oops. All right, so if we use letters, A over B equals C over D, we can say that when we bring D up and multiply it with A, we have AD, and bring B up and multiply it with C, we've got BC. Why do we have this little section in the rule? When B and D do not equal 0. Why do we have that there? Anyone else? Anyone else? Okay, Lexi. Right, whenever we have a rule and you have a variable in the denominator may not equal 0. What do we call the fraction when the denominator is 0?
Undefined.
Everyone say it?
Undefined.
Undefined. Okay. All right, so we used cross products in your assignment yesterday. We're going to see some, starting off here, this is a rather simple one, but we're going to get a few that are a little more complicated, as you can see in number B here, or question B. So let's go ahead and use cross products, even though this A could be solved just by blowing it up, right? Because what is the factor we could multiply 4 by to get to 12? 4 times 3. So, if we look at it in reverse, 12 divided by 3 is 4. So 24 divided by 3 is 8. So we know the answer should be 8, but how can we write this using cross product? Chris?
I simplified 12 over.
Oh, good for you. Okay, we talked about that yesterday. So what is 12 over 24?
1/2.
Good. Much
And
nicer.
then I did 4 times 0.
Now you can bring the 2 up and call it 8 equals
1x.
1 times x. And there you go. It's done. All right. How about B? What makes this one really, really tricky? Tessa?
Well, in a denominator, that's on the first one, we use the distributive property.
Okay, so she says the denominator has x minus 4, so the entire quantity needs to come up and be multiplied, right? So bring it up, and we call it 3 times x minus 4 equals 9 times x. So Tessa said it correctly. We've got to use the distributive property, right? And so what do we have when we do?
3x minus 12.
3x minus 12 equals 9x.
And then you subtract 3x from both
So
sides.
subtract 3x. Good.
And you get 3x.
get what?
3x.
What's left on the left side?
Um,
Over here.
negative 12.
And 9x minus 3x. 9 minus 3.
Oh, 6.
6x, good. And to finish it, we just divide by 6. And we end up with,
-2.
good job, equals x. Okay, and so if we go plug that in, the original, let's look and see what it looks like. 3 over -2, does that equal 9 over -2 minus 4? What is -2 minus 4? -6. So this on the right is 9 over -6. Is that the same as 3 over -2? And it is, right? We could simplify, reduce it, and see that it is. So we have checked this solution and it works, okay? Try another one on your own and come back and check it when you've tried it. Actually, there are 2 here. They're a little challenging because we've got these 2-part denominators or numerators. They're called binomials. Okay, so he brought the entire x minus 6 up and multiplied it to 3. Now he's distributing. He's collecting his variables to one side. And because the variable is negative, he's dividing by -1. So x equals 18. Thumbs up if you agree. Good, good job. And how about 3? Does somebody want to volunteer there? Okay, Dylan? Okay, so Dylan is showing that he's distributing the 5 to both terms, m minus 6. He's doing that multiplication without showing it. You see that? Now he's... Are you allowed to what? Sure, you could. You could move the right ratio to the left side. Because it's an equation, you can do that if you're more comfortable with that. He added 30 to both sides. Now he's subtracting. So he actually waited to collect his variable, I think, because he wanted to subtract 4m and he didn't want to leave 0 on the right. So he's showing this all in one step. 1m is left, equals 30. Thumbs up if you agree. M equals 30. So when we talk about proportions, we often talk about scales, scale drawings, right? And what is a scale drawing? How many dimensions is a scale drawing, Tatum? We have such a thing as a scale model, and then we have scale drawings. So a drawing has how many dimensions? A piece of paper has how many dimensions? Well, okay, it has a tiny bit of depth, but we usually think of it as a flat surface, so 2 dimensions. 2 dimensions, okay? But if I was to build a little model of, let's say, our school, then how many dimensions would it have?
3.
3, okay? So a scale drawing is 2-dimensional. That's proportional to actual life. So we always want our proportions set up with values in this way. Consistent manner. Model over actual equals model over actual. If we get a scale that shows us model over actual, and then we take some numbers that show actual over model, this would be a not true way of setting up the proportion. This would be untrue. So we have to be really careful when using the scale that we understand that we're going to put the model over actual in most cases. Okay, so it's a true statement that we're creating. All right, so this is a question from the guided practice from your book about model ships. And notice it says the ship model kits sold at a hobby store have a scale of 1 foot to 600 feet. So which of those two numbers represents the actual boat? Everyone?
600.
600 feet. So 1 foot on this model is 600 feet for the actual boat. A completed model of the Queen Elizabeth II is 1.6 feet long. We're asked to estimate the actual length of the Queen Elizabeth II, the actual boat, ship, right? So we want to create this proportion, and the first thing we have here is the scale that's given, right? So how shall we write the scale given? Bella?
600.
And let's go ahead and keep the units so we know what we're working with. 1 foot over 600 feet. Well, actually, do we need the units? Because scales, in this case, this is in the same units, right? So 1 to 600. Anyway. And then we're going to place the information we know in the second ratio. What do we know? Do we know the model, or do we know the actual life size? Chris?
We just do the model.
So where do we put it, in the top or the bottom of this ratio?
The top.
Good. So we put 1.6 feet across from the model in the scale. The model is in the numerator, so we have the model in our known information. And we have this unknown down here, which we could just call our EX. How about Q for Queen Elizabeth II? Okay. So it's up to you. You can call it whatever variable you like. And so now we can use our cross products to solve, right? Once again, the feet over here just equal 1, feet over feet. So when we bring the Q up here, what's Q times 1? Just Q. So this is not a tough one, right? We're going to bring the 600 up here, and we end up with 600 times 1.6 feet. And our answer will be in feet. Okay? So go and work out what is 600 times 1.6. Have you worked it out? Anthony? Anyone else get that? 960? Good job. 960 feet. Okay, so does this seem reasonable to you?
Yes.
If 1 foot in the model equals 600 feet in the real ship, then 1.6 feet, a 1.6 foot model is going to be longer than 600 feet. It's going to be 960 feet. So this makes sense. That seems reasonable. Okay? Questions on that? So when you're setting up your scale, be sure that you know that you have model over actual equals model over actual. You could flip it though. Most often we get model over actual. If you flip it and have actual over model, what will have to be the case over here? Actual over model. Okay, so you've got to have consistency in your ratios, okay? And that's your assignment for today.